proper test, these are the equipment that you're going to use for the proper test. This is the mold, and this is the hammer. So you pour the soil here, and put this the tip on the surface of the soil, and you drop it. Okay, and you repeat this dropping the hammer for the one layer, and once it's completed for that layer, you're going to put another soil mass and then do it for another layer. Okay? And so, as I said, the compacting effort affects the soil density, the reducing density. So then we have to specify this hammer size and the dropping height and the mold size. Right? So that's all. There's a standard specification for that. So what we're going to talk about soon. And what find the mass of the hammer. And the height of drop. What else can affect the dry density? Number of drops. We need to specify the number of drops. And what else? The number of layers. If you do it for a very thin layer, then it will be very compacted well. So that you can repeat the procedure many, many times. But if you do maybe one or two layers, then the compaction with the same amount of this compacted effort, the resulting dry density will be lower. So the number of layers. And the last thing is the mold volume. Volume of mold. So these parameters are all specified by this engineer for the structure. So he specified this mass of hammer, height of drop, number of layers, mold volume, and the develop the procedure. So this is this procedure. And in the end, the resulting graph that you're going to get is the graph will look like this. So this is the water content, x-axis will be the water content, and y-axis is dry density. So when you have good compaction, dry density will be larger. Right? When you have poor compaction, then the dry density will be low. And generally shows this kind of graph. And the maximum value here is for the maximum dry density, rho d max. And the water content that results in the maximum dry density is called the optimum water content. W sub OPT. So then let's find out how the procedure of this standard of the test. Mold. We'll have a 3-layer. And the volume of the mold is 1/30 cubic feet. So if you convert to the SI unit, then it's 944. And as I said, in the standard of the test, we compact the soil in 3 layers. number of layer n will be 3. And drop the hammer. The height h will be 1 feet. Let us 30.5 centimeters. It's about is long and the weight. Is 5.5 pounds. So that's about 495 kilograms. And about 47 newtons. Okay, so 5.5 pounds. And number of blows, so apply 25 blows per layer. Then to N, large N will be 25. And when you compact the soil to make it flat, you look at from the top. So you dump the soil first, and first 4 blow will be like this. One blow, 2 blow, second, third, and fourth. After that, I'm gonna go around it. 5, 6, 7, 8, 9, to make it 25 loaves. That's the common way to do the compaction for the one layer. You can, so you're gonna go as a spiral. So, the compaction is affected by what the dry density, with water content, and compactive effort in the soil type, right? And we can specify, we can calculate the specific energy applied to take the compactive effort. Thank you. And the specific energy for the compactive effort is E sub C. And this energy will increase with number of blows, right? And what are the other things? The energy. What about the kinetic energy? The height times mass and gravitation acceleration, right? So the kinetic energy will be weight times the height. So the W times height. And what about number of layers? When you have more layers, compaction will be more efficient. So the number of layers will be proportional to the compactive effort, and the volume will be inversely proportional to the compactive effort. So this is the very simple equation to calculate the specific energy applied to the compaction. And then let's calculate. Let's calculate the numbers. N, what's the large N? 25. And W? In Newton? 24.47 Newton times height. 0.3 meter. 0.305 meter. And number of will be 3. And the volume is, how much is the volume? 944. That's cubic centimeter, right? If you want to convert it to the square cubic meter, we're using cubic meter here, then 10 to the negative 6 cubic meter. 5, 9, 2.7 kilojoule per cubic meter. Which one is correct? I don't know. But you get the idea. It's pretty much a similar number. Which one is correct?
592cm.
Oh, is this the correct? So about 593 kilojoule per cubic meter. So when you have moist soil and you compact it to 3 layers, 1, 2, 3 layers. And then you're going to have to measure the density. So first, how you measure the density? How can you measure the density? So say that the soil is filled up to this mode, you're going to measure the initial mass of this mode first. And then if you subtract this mass of mode from the total mass, then you get the total mass of the soil only, right? Without the mode. So from that, because you know the volume of the ball, so you can calculate the total density. Total mass over total volume. And then you're going to have to measure the water content. By oven dry the sample. So you scoop the sample and then put it in the oven. So you measure the dry mass. So then you can calculate the water content for that sort of scoop. Okay. By oven dry. And then, in the end, your purpose or the final objective is the dry density. Right? Using these two values, the rho T and the W, the water content, you can calculate the dry density. And if you're remembering this equation, the rho T over 1 plus W, the water content, then from there you can calculate the dry density. Then you're going to repeat for several water content. Water content. W/C is the water content. That's the symbol I use. I like to use. And then we can plot the curve, the rho D versus water content. And this is called the compaction curve. So the compaction curve, when you get the compaction curve, the curve will look like this. Let's try and see. And you get this kind of curve. Water content is the x-axis. And the maximum value is the rho D max, maximum dry density, and the optimum water content. So in general, you will have to do the experiment on the left side of the water content, maybe 2 points, and another 2 points at the right side of the water, the optimum water content. So the normally 4 to 5 water content tests will be required. And this is the optimum. Water content. And the right side of this W optimum water content is called as west side or wet oval. This is the maximum range. The typical range is and the optimum water content, maximum is 5 to 40%. Maximum range. Typical range is 10 to 25%. For fine grained soil, in general, the optimum water content is a little bit less than the plastic limit. Slightly. Optimum water content has been found to be slightly less than the plastic limit for the fine grained soil. So below the water content here, below the optimum water content, why this the dry density will increase as you add more water? Let's think about the phenomena, the foam scale, the particle scale phenomena. Like first, it's gonna be dry, and as you add the water, the dry density, so the void ratio will decrease, right, for the same amount of energy you're putting in. So why this water is doing something? Probably the water is surely doing something, and how it acts? How does it act to the soil? Force. Okay. So as you add the water, you're developing the capillary force. And what's the capillary force? That's gonna bind the grains together so that they can stick together. Right? So in the dry side, when you add the water, you're developing capillary pressure. And that's how the soil can be obligated by themselves, among themselves. So that in the end, the dry compaction, the dry density will be higher than the case we don't have any water. What about the dry side, the wet side then? Now, you're adding more than the optimal water content. Now, with the same amount of the compacted effort, it's resulting in the higher void ratio and the lower dry density. Actually, when you add too much water, now it's starting to replace the position of the volume filled by soil. So that the water starts to replace the particles in the mold because the density of the water is less than the solid density. So that in the end, the resulting total dry density, overall dry density becomes less than before. So now the water is getting too much, so that the grain cannot penetrate and make cannot be more squeezing. That will be more reasonable. So we've been talking about the standard proper test, and there's a modified. This is for heavier compaction equipment. historically, in 1920s, there were not much heavy equipment for the compaction, but recently the heavier compaction equipment has been developed, so that the procedure with higher compactive effort was required. Instead of using the standard hammer, they increase the hammer weight. To 10 pounds. So that's about 4.45 kilograms, 54, and also increase the drop height. 18 inches. That's 457 millimeters. And instead of 3 layers in the modified process test, you use the 5 layers. And the same number of blows, 25 blows. And the same mode. Volume is still 944 cubic centimeters. So in the modified process test, actually, as people develop the heavier equipment for that compaction, field compaction, the standard test was limited by the drop of the weight and drop height of the standard procedure. So they modified the test for simulating the heavier compaction equipment. So when you calculate the compacting effort, and time, weight, height, and the number of layers or the volume, that's about 2,692 before the comparing to the standard of the test, it was about 950, 953,
593.
593, 593 kilojoules, much larger compactive effort. So when you increase the compactive effort, the graph changes a little bit. Content, dry density, and before. So here, this is from the standard of the test. And when you increase the compactive effort, this amount, this curve will be shifted to upper side. Right? You get the higher dry density, and also the optimum dry density goes a little bit less. So you get this kind of curve. From standard process test, and this will be optimum water content from modified test. And if you increase more the compactive effort, the curve will be around here. So it's going to go up and shift it to the left side. So if you get the several compaction curve with different compactive effort, can draw the line to the maximum value. And this is called as line of optimum. And the difference between the optimum water content from the standard and the modified test is about 3 to 5%. It's not that much, 3 to 5%. So if the compacted effort increases rho d, maximum dry density increases, and optimum water content. And the last one is there is a theoretical curve which is almost parallel to this line of optimum. Around here. But it doesn't touch the compaction curve. This is called as zero error void curve. So in short, AB curve. Zero error void. And this is a theoretical curve assuming that there is no air inside the solar mass. So this curve represents the fully saturated condition. This is when the regular situation is here. And we're going to talk about this CAV curve more in the next class, or how we can draw the CAV curve theoretically from the equation. Zero air void curve is the CAV curve. And this is a theoretical curve that represents the fully saturated condition. So we are finding the dry density and the water content relation when the degree of saturation is 100%. And it's a theoretical curve because it cannot achieve by compaction. And so you can just only calculate it. Right? And here, where is it? It's like getting rho d and W relation when degree of saturation is 1. And we know the dry density, and also dry density is defined as the solid density over 1 plus E void ratio. And we know this relation at least, SE equals W times GS. So from there, here we don't know the void ratio, so we can replace it with the known value here. So then you get this equation. Very simple. So rho d is GS times water density times S over S plus W times GS. Here if you calculate the GAV, you can assume the S is 1, right? So this will be 1 and this will be 1. So rho W GS over 1 plus W GS. Rho d. Right? We know the water density is 1 gram per cubic centimeter, and GS will be given, maybe it's going to be like 2.7 over 2.65. Right? So then you can plug the water content from like 10 to 20%, then you get the dry density. Right? And from that result, you can plot it
in this the rho d versus W graph, here when the degree of saturation is 100%, and if you put the S as 0.8, then you get the another curve for representing the degree of saturation of 80%, and 60%, you can do the same thing, right? So if you plot it with the standard Proctor test result or the modified Proctor test result, you get this curve. So this is the GAV curve, and line of optimum is the line that connects the maximum dry density, right? That will be the line of optimum. In general, GAV and the line of optimum, can you say line of optimum are almost parallel each other. Then where will be the water content, the optimal water content? Optimal water content is here, right? W opt, and here is another W opt from the modified Proctor test and from the standard Proctor test. I think in the lab you didn't do the modified Proctor test, but still you can get the compaction curve from the standard Proctor test, the lower curve like this, and you can draw the GAV curve for the degree of saturation, 100%, 80%, and 60%. And by comparing this line of optimum to this GAV curve, you can kind of think that the line of optimum locates between like 70% of degree of saturation to like 80%, right? So this is about 70% to 80%. So that's the optimal condition for the maximum compaction.